Welcome to the Explainer. So if you've ever flown a drone, you already know that keeping it up in the air is this relentless, ongoing battle against the two ultimate enemies of flight, gravity and power drain. It takes an immense amount of energy just to defy gravity, right? And managing that energy correctly, well, that's literally the absolute difference between a successful mission and your drone just tumbling out of the sky. So let's just start by asking a fundamental question. What actually keeps a drone in the sky? I mean, sure, on a basic level, you've got propellers pushing air downward. We all know that. But to truly wrap our heads around power management, I want you to think of a drone as a living, breathing machine. It's got an anatomy. It has a heart that pumps raw energy, veins that distribute that lifeblood, and muscles that do the heavy lifting. Today, we're going to dissect that exact anatomy.
Here's our flight plan for today. We'll look at the heart, which is battery chemistries, then capacity versus weight trade-offs. After that, we'll map out the veins, the power distribution, and finally, we'll cover maximizing your drone's energy efficiency.
Let's dive right into Section 1, the heart, focusing on battery chemistries.
You'll notice a pretty stark contrast between our main power sources here. Lithium polymer, or LiPo, are the undisputed kings of modern drones, especially for racing and aerobatics. Why? Because they're lightweight and can deliver these massive high-discharge bursts of power. But you really have to respect them. They can be volatile if they get damaged or overcharged. Then we have lithium-ion. They've got a lower discharge rate and they're a bit heavier, but their total energy storage over time is vastly superior. That makes them the absolute go-to for endurance missions like agricultural mapping or surveying. Finally, down at the bottom, nickel metal hydride, or NiMH. They're incredibly stable, but because they're heavy and hold a lot less energy, you're mostly just going to see them in educational or beginner hobbyist drones these days.
Now, to understand exactly how much juice these batteries hold, we have to look at capacity. You'll see mAh, which stands for milliamp hours. I want you to think of this quite literally as the size of your drone's gas tank. So the crucial takeaway here is that a 2200 milliamp hour battery can, theoretically, provide 2200 milliamps of current for exactly 1 hour, or 1100 milliamps for 2 hours. It is your drone's energy reservoir. But as you might guess, simply strapping a bigger gas tank onto your drone isn't always the smartest play.
Which brings us perfectly to Section 2, capacity versus weight trade-offs. This is the ultimate engineering dilemma. On the one hand, you have high capacity. If you add a massive, heavier battery, you are undoubtedly going to get a longer flight time. That's perfect for a survey drone that needs to methodically map out a giant field. But that extra weight absolutely ruins your speed and responsiveness. Your motors have to work overtime just to keep the thing aloft. On the flip side, we have high agility. For a racing drone, you want the lightest battery possible. Sure, you sacrifice flight time, you might only stay airborne for 3 or 4 minutes tops, but you gain explosive speed and unmatched maneuverability.
Alongside capacity, we absolutely have to talk about voltage. You're going to see numbers like 14.8 volts all the time in drone specs. Why that specific number? Well, here's a neat little insider trick. Drone batteries actually group individual 3.7 volt cells together in a series. So when you see 4S on a LiPo battery, it simply means 4 of these individual cells are chained together. 4 times 3.7 gives us exactly 14.8 volts. Pushing this higher voltage is actually a brilliant engineering trick, mostly because it significantly improves motor efficiency and gives you way faster response times.
Okay, now let's decode one of the most vital, yet honestly most misunderstood numbers on a battery, the C rating, or discharge rate. This dictates how fast you can safely drain that gas tank without doing permanent damage. The math is straightforward, but it is critical. If we take our 2200 milliamp hour battery, which is 2.2 amps, and it has a 25 C rating, we just multiply 2.2 by 25. That means this specific battery can safely deliver a massive 55 amp burst of current. If your C rating is too low for your aggressive flying style, you're going to experience what's called voltage sag, overheating, or worse, a total battery failure mid-flight. No one wants that.
Moving right along to Section 3, the veins, or power distribution.
Let's trace the exact path of our power. We've got our raw, beating heart of a battery. Now, how do we safely route that massive 55 amp burst of electrical energy all the way to the muscles without causing a mid-air electrical fire? Step 1, energy leaves the battery. Step 2, it hits the power distribution board, or PDB. This is basically the central hub, usually a flat circuit board sitting right smack in the middle of the drone frame. Step 3, the PDB cleanly splits that raw power out to the electronic speed controllers, the ESCs. And finally, Step 4, the ESCs inject that power directly into the spinning motors. When built correctly, it is a beautiful, highly efficient circulatory system. But, of course,
there's a catch. Remember our 14.8 volts? If you push almost 15 volts directly into a delicate flight controller or a sensitive GPS module, you will instantly fry them. They usually only need 5 or 12 volts to run, so we use voltage regulators. Now, linear regulators are kind of the old way of doing things. They're simple, but they are incredibly inefficient because they literally just burn off that excess voltage as raw heat. What you actually want are switching regulators, also known as buck-boost converters. They efficiently step the voltage up or down with minimal heat loss, protecting your sensitive electronics while conserving your precious battery capacity. Next in line are the ESCs, the electronic speed controllers. If the battery's the heart, the ESCs are absolutely the nervous system. They don't just dumbly dump raw power into the motors, they precisely regulate it. Modern ESCs use incredibly fast digital protocols, things like BLHI or D-Shot. These protocols translate commands from the flight controller thousands of times a second, instantly adjusting the RPM of each individual motor to keep your drone perfectly stable even in really heavy winds. And hey, a healthy circulatory system needs strong vanes, right? You need thick 12 to 16 AWG wires to handle all that high current from the battery without literally melting. You also need highly secure XT60 or EC5 connectors so mid-air vibrations don't cause a sudden catastrophic disconnect. Plus, you need LC filters. Why? Because high-powered motors create electrical noise that can literally blind your GPS or completely scramble your video feed. LC filters clean that noise right out of the lines. Oh, and for commercial or industrial drones, we even use dual batteries and redundant systems just to ensure a single failure doesn't equal a crash.
All right, let's move into our final section, maximizing drone energy efficiency.
We've built the anatomy. Now let's talk about the metaphorical diet and exercise required to squeeze every last drop of flight time and performance out of your machine. It starts right at the hardware level with your propulsion system. On one side, we have the recipe for maximum efficiency: large, two-blade propellers paired with low kV motors. As a quick refresher, kV refers to revolutions per minute per volt. This low kV setup moves a massive amount of air slowly and efficiently, which is perfect for long-endurance hovering. But if you want maximum thrust, you do the opposite. You pair small 3- or 4-blade propellers with high kV motors. They spin incredibly fast, they bite into the air aggressively, and they give you amazing agility and punch, but they will greedily consume power and drain your battery in minutes.
So, how do we fly smarter? Let's run through some really actionable pro tips to maximize your energy efficiency. First up, pilot behavior. Try to maintain a steady 50 to 70% throttle. Constantly punching the throttle wastes massive amounts of energy. Second, reduce your weight and improve aerodynamics by using streamlined, lightweight carbon fiber frames. Third, plan your flights out. If you're mapping, fly smooth, automated grid paths to minimize energy-wasting sharp turns or sudden altitude changes. And finally, battery care. Even the absolute best drone will fail if the battery degrades. Never leave a LiPo fully charged or fully depleted for weeks on end. To extend their lifespan, always store them at a balanced 3.8 volts per cell in a cool, dry place.
I want to leave you with a quick look at the horizon. We've talked all about LiPo and Li-ion, which totally dominate the market today. But what happens when emerging technologies like solid-state and lithium-sulfur batteries hit the mainstream? These ultra-dense chemistries promise far more power at a fraction of the weight and with dramatically improved safety. So how will they soon shatter our current weight-to-power limitations? I mean, imagine drones that can fly for hours instead of minutes, securely carrying much heavier payloads, completely revolutionizing unmanned flight as we know it. It is an incredible time to be watching this space. Thanks for diving into the anatomy of drone power with me today.